Okay, let's see if I can make this again without catastrophically failing. This is problem 3 for tutorial 3, and a lot of the stuff, a lot of the key points I think were already covered in parts 1 and 2. So I'm just gonna, the only thing I'm gonna do here is calculate the reactions for you, because I think once you have the reactions, it's very easy to figure out the problem and solve. And I'm gonna show you where you should take your cuts, because if you take your cuts in a certain way, you can actually, well, not ignore, but the interesting stuff that happens at point B can be neglected. Yeah, because point B is gonna, because it's kind of similar to here, except here you were just worried about, you could just follow the thing. You didn't have to worry about like which direction does the moment apply, like any you didn't have to worry about some of the details. All the details, however, are present here. So yeah, let's go jump right into this. If I do this properly this time, I will know how to. Okay, so you have triangle load. I'm not drawing this to scale at all, but you know, this is 2 kilonewton meters. This is 4 kilonewton per meter, and it goes down to 0 here. So it should be more like this. I didn't draw this very well, but that's okay. This is your y, and this is your x. This is 2.814. Now, I'm gonna just make a small estimate here. This is actually 1.98 or 1.99 or something like that. I'm just gonna say that this is 2 and this is 2. Instead of having to deal with decimals here, you guys should be exacting your notation, so that'll change your answer very slightly. But yeah, yeah, I don't know. I'm just gonna neglect this to make life much easier. Now, to get the reactions, you have a roller here and a pin here. I am going to take the moment about point B, and the reason why I'm going to do that is if I do it that way, then I don't have to, Cx is not going to come into play, and dy is not going to come into play. And with that, the only unknown I have is cy. And having only one known means I can solve for that directly. So let's go ahead and get started, and I shall make sure that I calculate the moment properly this time. Here is moment about point B. And we're gonna break this up into 2 triangles. And I'm gonna do that because it's not hard, but it's tedious to find the center of this triangle, of this one big triangle. So if I break it up into 2 small triangles, then for the triangle on the right, I have for my total load, I have 4 times 1/2. And this acts at a distance of 1/3 times 4 away from point B. Now I have cy, and as usual, I assume cx and cy act this way. I'm going to assume that dy acts this way. My cy term is going to be minus cy times 4. I'm going to have a 2 here. Remember what I said earlier, it doesn't matter where this thing acts, because I have an applied moment, I just need to add 2. I don't need to worry about multiplying it by any distance, any fulcrum or anything. It's already in terms of force times distance. This is force times distance, force times distance. This is force times distance already, so I don't need to do any other terms. And then let's look at the other triangle. The other triangle is going to be 4 times 2 times 1/2 times 2 times 1/3. And I went a little bit off the page here, so I'll just write that again. 4 times 2 times 1/2 times 2 times 1/3. This is your distance, and this is your load. And finally, you have one last term. This is the minus 2 times 2. Now if you do all of this, I'm not going to do the math for you, I'm just going to give you the final result. This becomes Cy equals 1.5 kilonewtons. Now remember what I said earlier, you can just use sum of forces Fy, you get dy equals 10.5 kilonewtons. Let me explain how I got this. I got this by doing 4 times 6 times 1/2. This is your total Y load, and this is equal to 12. 12 minus 1.5 gives you dy. dy equals 10.5. Okay, and then your f of x term. You might be wondering, well, I took into account this 2 for the y forces. Do I need to take into account this 2 for the x forces? And the answer is no. Once you've taken care of it in the y forces, you can just use your sum of fx equation like always, and you don't need to worry about it anymore. So your sum of fx is going to be 2 plus cx equals 0, cx equals negative 2 kilonewtons. Okay, now that we have that done, let's look at where you should take your cuts. I'm gonna recommend that you take your cuts. Let's look at point A first. If you take your cut here, so this is your load, this is your cut, so you have let me use different markers here. You have V, you have M, and you're gonna have axial load N. Then for your other side, I recommend that you take your cut this way. And then when you do that, you're going to have M prime, and you're going to have V prime, and you're going to have N prime. And finally, for the last load, I recommend that you start from the bottom and work your way up. Yeah, for the bottom one, you're actually going to have you can, I don't know if you feel comfortable enough drawing this, but you technically need 2 cuts here, but yeah. I always, okay, so yeah, let's do it with 2 cuts. You're going to use 1 cut from there. This is from the base before you get to the top, and you're going to have your, like always, you're going to have your moment, and you're going to have your shear is going to act this way, and you're going to have your technically you're gonna need a third equation, I realize, but it acts very similarly to the example I did in the last problem. So you can just look at that. Anyway, if you do it this way, then your forces at point B, you'll notice that you don't have to worry about point B at all, because it just doesn't appear. And because it doesn't appear, you don't have to deal with all the interaction equations. You don't have to worry about transferring moments or loads or anything. You can just calculate each of these arms individually and then draw your diagrams. And then remember, I already showed you how to draw diagrams. You're supposed to draw the original diagram.